Hello students, now we are going to discuss the main important chemical properties of boron family, that is group 13 elements, their chemical properties. In the last class already we discussed the physical properties of boron family. So what are the chemical properties, what are the properties, main properties shown by elements of group 13, let us discuss. First, see that action with oxygen, with oxygen mainly, group elements when reacts with oxygen, generally reaction takes place on heating. Some require strong heating, some require less heating, produce oxides, M2O3. These are the formula of oxides. With the oxygen on heating produce oxides. A general formula is M2O3. This is the formula of oxides. Okay? And the reactivity order, if you see, boron less than aluminum, less than gallium, less than indium, less than aluminum. That is increasing order of reactivity due to low emission energy, large size, so many factors. That's why the reactivity increase. Then what are the nature of oxides? If you see, your boron oxides, B2O3, this is acidic character if you compare. This is your high acidic character. Then aluminum oxide, then your gallium oxide, then indium oxide, then thallium oxides. You see, but this is acidic nature. Okay, but here you remember this B2O3 is almost acidic. It is acidic, but aluminum oxides and gallium oxides, these two amphoteric. And your indium oxides and thallium oxides, you see, these two are basic. So you have to remember this. This is a very important difference. If basic question will be asked, which is most basic, that is thallium. Which is most acidic, that is these two. Most acidic is most basic. And this aluminum, gallium, these two are amphoteric character. If you see the reactivity, that boron reacts with base, forming sodium borate, Na3, BO3 plus water. But boron oxide does not react with HCl. It becomes acidic. It has no reaction with HCl. B2O3 HCl, no reactions. But your aluminum oxide with NaOH forming sodium meta-aluminate and water. Sodium meta-aluminate, NaLO2. And these aluminum oxides also reacts with hydrofluoric acid, produce aluminum chloride and water. That means it shows acidic character and basic character. But boron trioxide only shows acid nature. So these are very important comparison of action with the oxygen forming oxides. Then with water. With water generally boron has no reactions. Boron with water generally do not react with water. No reaction generally ordinary temperature because it cannot displace hydrogen. That's why boron has no reaction with water. But aluminum metals or high reactive gallium, indium, thallium, they react with water on strong heating on strong heating produce aluminum hydroxide or aluminum oxides and hydrogen gas. Produce this aluminum oxides and hydrogen. So that is it reacts with water forming aluminum oxides, and gallium, thallium, indium also produce oxides and forming hydrogen gas. So action with, if you see action with metals also, reactivity is this order: boron less than aluminum, less than gallium, less than indium, less than thallium. In this order, reactivity with waters. Okay, with water, with hydrogen. With hydrogen, boron with hydrogen on heating produce borans. Different types of borans. Borans generally two types of boron. The general formula is BnHn plus 4. This type of boron is produced, or BnHn plus 6. This type of boron. Two types of borans are produced. For example, boron H2 produce B2H6. This name is diboron. It is called diboron. The structure of B2H6 is this is a banana shape. The banana shape, this is bridging hydrogen. This is a common hydrogen between two bonds. Here what happens? You see two BH3 combines. This is produced due to formation of two BH3. Two BH3 combine to form this. One is dative bond because boron has vacant orbitals. Another is that dative bond. One dative bond, one dative bond, one normal covalent bond. One normal bond, one alternately dative bond and covalent bond is formed. So it exists in banana shape. It is called banana shape. Diboron. Banana shape. This is called diboron. This is called diboron. Okay. So mainly boron reacts with boron or others also forming hydrides. Boron produces boron, that aluminum, allen, gallen, indium, thallen, like this types of hydrides. Boron or boron family elements reacts with hydrogen on heating, forming hydrides, forming different types of hydrides. And mainly almost all hydrides exist in that dimeric forms due to vacant orbital, availability of vacant orbital in aluminum or boron compounds. Okay, so this is your diboron, and this diboron, if you see on heating, if diboron will be heated on oxygen bonds on heating, it also bonds produce boron trioxides and water and produce heat. Large amount of heat also produce diboron, and it is also highly combustible. Diboron also combustible and produce blue flame when heated and produce blue flame. So this is the some important reaction of boron family with hydrogen. Then very important is with halogen. Means H2. Generally metals which reacts with halogen or heating forming MH3, forming halides MH3, having +3 oxidation state, having +3 oxidation state of elements. What are the examples? Boron produce BF3, BCl3, Br3 and Vi3, and almost all halides of boron, all are loose acids, are called loose acids. These are called loose acids. Why they are called loose acids? Because they have vacant orbital. All boron having vacant orbitals, that is p orbitals, so it behaves as a loose acids. Due to loose acidic character, if you compare the loose acidic character, the character BF3 is the least acidic compared to BCl3, compared to Br3, compared to Br3. Why? Planar set. Because if you draw the structure, what happens? This is your boron having lone pair, three lone pair. Then what happens? And boron has vacant orbitals. Then what happens? A p pi bonding, that is back, that is called back p pi bonding takes place. Back p pi bonding takes place between boron and fluorine. That's why the electron deficient nature of boron is satisfied. That's why it will not behave as loose acid, or the acidic character of BF3 will be least. Why BF3 is the least acidic? This acidic nature. Acidic nature. Acidic nature of BF3 is least due to back p pi bonding. That means after formation of sigma bond, a pi bond is formed between fluorine and boron due to p pi bond formation. That's why the acidic character of BF3 is least. That is a very important question also. And aluminum chloride, similarly if you do two molecules of aluminum chloride and also combine forming Al2Cl6, and the structure is same structure. Here fluorine, dimery form of aluminum chloride. It exists in dimery form due to this vacant orbital, availability of vacant orbital in aluminum existing dimery. Just like already discussed, diboron, same dimery form of BST and dimery form of AlCl3, Al2Cl6. Almost, if you see, these all halides, almost all are common, all halides are covalent nature, except aluminum fluoride. Almost all halides generally covalent character, because possibility of aluminum 3 plus only possible, 3 electron can be removed from aluminum only by fluorine due to high electronegativity. That's why aluminum fluoride is ionic. Except means it is ionic. But almost all aluminum chloride, aluminum bromide, B fluorides or halides of boron, all have covalent character. Because boron cannot lose 3 electrons, because due to high ionization energy, I1, I2 and I3, the 3 ionization energy of boron is very high if you combine. That's why boron cannot lose 3 electrons completely. Only it produces covalent bonds. So all halides of boron family elements, almost all are covalents. And stability, you see, stability of fluorides, if you compare, that your thallium triiodides is almost impossible. Thallium triiodides generally does not exist, because thallium generally shows plus on oxidation state, and thallium triiodide is very unstable. That's why it is decomposed. That's why thallium triiodide generally unstable, does not exist. If you see the stability. So this is the formation of halides with halogen, hydrides with hydrogen, oxides with oxygen, and nitrides also, formation of nitrides. If you see, with nitrogen, they produce, with nitrogen on heating, produce nitrides, Mn, produce nitrides. Remember, very important is boron nitride. Boron nitride is very strong, very hard, hardest also, and very high melting point. Boron nitride, just like diamond, boron nitride, very hardest substance, boron nitride. And boron, so aluminum, that boron family reacts with or heated with nitrogen, forming nitrides. And these nitrides also, for example, aluminum nitride, when reacts with water, forming ammonia gas. This is very important. All nitrides of this boron family, when reacts with water, dissolve in water, forming ammonia gas, release ammonia gas. So this is the nitrides, halides, and the comparison of acidic character of all halides. Generally, remember, all boron compounds behave as Lewis acid because due to availability of vacant orbital on boron. Boron hydrides, boron halides, almost all are Lewis acid, behave as Lewis acid. Okay? With acids. Generally, boron do not react with halides, halogen acids. Do not react because boron is the least reactive. It cannot displace hydrogen from acids. That's why boron does not react with hydrochloric acid because it cannot displace hydrogen. But boron when reacts with concentrated nitric acid on heating produce boric acids. It produces boric acid, BOH, boric acids and NO2. Boric acids and NO2 is produced. Similarly, but aluminum reacts with nitric acids, forming sodium metaluminate. This is aluminum oxides. It produce aluminum oxides, NO2 and water. And due to formation of nitric acid, that is aluminum oxide, very stable. This is very stable. So almost passive. Aluminum is passive for nitric acid due to formation of stable oxide layer, aluminum oxide layer. That's why aluminum do not react with nitric acid. Nitric acid can be stored in aluminum vessel because due to formation of stable oxide layer, it does not react further. Aluminium also and other indium, thallium is also very reactive towards acids. But reactivity towards boron is least. If you see the reactivity, boron less than aluminium, less than gallium, less than indium, less than thallium. This is the reactivity towards. Generally it reacts with acids, but the reactivity generally increases. Next very important thing is, now we will discuss, that is action with base. Okay, to complete this one with the base. Boron generally do not react with base at room temperature, but on strong heating produce sodium borate and hydrogen gas. Only at a very high temperature, above 700 degrees Celsius, above 700 degree Kelvin, under high temperature, it reacts with base forming sodium borate. and if you see the aluminum reactivity is very high towards base and presence of dilute medium, it reacts with aluminum forming sodium metaaluminate and hydrogen gas. Gallium also reacts, but aluminum reactivity is very high compared to boron, forming salt NaAlO2. This is NaOL2. Sodium metaaluminate. It is called sodium metaaluminate. Salt is formed and hydrogen gas is formed. So action with this. But already we have discussed the oxides, and if you see the hydroxide, both are forming hydroxides. BOH whole 3, AlOH whole 3, and gallium OH whole 3, indium OH whole 3, thallium OH whole 3. If you see, and this is acidic, and these two amphoteric, like your oxides, and these are basic character, hydroxide basic character, and this is a, and boron trihydroxide, it is also called boric acid. It is also called boric acid. Other name is called boric acids. But when it dissolved in water, boric acids, when dissolved in water, forming BaOH whole 4 complex minus and H plus, and this H plus is produced from water. It is produced from water. That's why BOH whole 3, it is no doubt it is acidic because it produces H plus, but it is non-protic monobasic acid. Very important. Why it is monobasic? Because it produces one H plus. Or why is it non-protic? Because H plus is produced from water, not from BOH whole 3. That's why it is non-protic. It cannot produce free H plus ion. H plus ion is produced in presence of water from H2, from water. That's why BOH whole 3 cannot produce H plus ion. That's why it is called non-protic. No H plus ion. But monobasic because it produces one H plus ion. And this BOH whole 3, aluminium hydroxides is amphoteric nature. It is acidic. Your BOH whole 3 reacts with base, produce salt Na3 BO3 plus water. Salt is produced. But aluminium hydroxide, it is amphoteric, like your oxides. It is produced with base, producing NaAlOH whole 4 minus, and salt is produced, complex salt, and it also reacts with acids, forming salt, aluminum chloride and water. So aluminum hydroxides, aluminum oxides behave as amphoteric character, reacts with acid and base, forming salts. And it is also observed that boron can show covalency 4, maximum 4. Covalency of boron is maximum 4. Maximum 4 covalent source. For example, this one BOH whole 4, covalency is 4. But aluminium source more than 4. Aluminium AlH2O whole 6 is also produced. That's why it is aluminium hexa, aluminium this, it has covalency 6. So aluminium can show higher covalency, but boron shows only covalency 4. So these are very important properties of boron family. So you practice. Any doubt you have, you can ask me. Okay? Thank you all.